Hello, everyone. My name is Atul Kedia. I'm a sixth-year PhD candidate at the University of Notre Dame, and I'm going to be talking about binary neutron star mergers of quark matter-based equation of state. My collaborators on this work are listed here. So let's get started. Firstly, the nuclear matter equation of state. So equation of state can be understood as the amount of pressure the nuclear matter exerts on its surroundings based on what's the density of the matter, the electron fraction, the temperature, and so on. But more simply, it can be assumed to be just as just a relation between pressure and density. So on the plot over here on the right hand side, there's a couple of such equations of state shown. The y-axis is log of pressure, x-axis is log of densities. As the density increases, the pressure increases. So currently, the equation of state at low densities, below the nuclear saturation density, is fairly well constrained due to progress in nuclear theory and observations. However, the equation of state at higher densities is not that well constrained due to difficulties in lattice QCD calculations. And in particular, whether there's a phase transition to quark matter is not that well understood. However, currently there exists a lot of models based on perturbative QCD and non-perturbative QCD predicting the equation of state if there is a transition to quark matter. And for our work, we focus on one such equation of state. So it's called the QHC, quark hadron crossover equation of state, prepared by Baim et al. 2019. So this QHC 19 equation of state, there's a couple of different variants of it based on what's the coupling constant between the different quark matter. And so these are all four equations of state, QHC 19, A, B, C, and D. How this equation of state goes is that below twice the nuclear saturation density, it's a simple extension of APR. For densities above 5 times the nuclear saturation density, a purely quark matter equation of state is assumed and calculated based on the Nambu-Journo-Lazinho model. In the region in between these two, so in the region where the transition from hadronic matter to quark matter happens, a smooth interpolation is performed, and that's a crossover region. So that's the equation of state in total, and you can see them the equations of state A through D plotted over here. A is the bottommost red curve, and D is in between here if you squint a little bit. And so basically all of them fairly satisfy the GW170817 constraints. And further, they also satisfy the mass radius relations expected for modern equations of state. So for our simulations, however, we take that equation of state and adapt it in a piecewise polytropic fashion, similar to Reed et al., but not identical to their scheme. In particular, we allow for a few more degrees of freedom in the densities. And so here in this slide, I'm showing on the plot on the left-hand side, I'm showing the parameterization for the gamma coefficients we obtain for QHC 19b. On the right-hand side plot, I'm showing the parameterization for QHC 19c. And it may be slightly different from the parameterization anyone would obtain using the same scheme as Reed et al., since we are using a few more degrees of freedom. So with that, I want to show finally the mass radius relation that we get for these QHC 19 equations of state. So for 19b, you can see that our piecewise and the raw 19b agree with each other. Same goes for 19C. The raw data and our piecewise agree with each other fairly well. And in all of them satisfy the twice solar mass cutoff for the nuclear mass. And so with that, I want to go into our mergers simulations. So we perform these merger simulations using GR Hydro on Einstein Toolkit. Initial data obtained by Lorene, generated by Lorene. And yeah, so let me just play these simulations. So these are for QHC 19c in particular, and for neutron stars described by 19c. And you can see that they merge, they in spiral and merge, and in their ring down, and then so in their final neutron star state, they stay for a much longer period. We performed the same simulation for 19b, and we noticed that for 19b, the neutron star state is, the merged neutron star state is very short. The binary, after merging, basically immediately collapses to a black hole. Whereas for 19c, it takes a fairly long time to collapse into the black hole. And so that is the main result for this talk, and I'm going to show that again over here. So on the plot on the left-hand side, I'm plotting, this is a plot of maximum density present in the entire simulation at any given time, at different times. And on the right-hand side, it's a plot of gravitational wave signature. We'll get to that in a second. But the maximum density present in all of simulation for the blue curve, which is 19b, and the red curve, which is 19c, they start at the same time, at the same place. So that's the maximum density present at the beginning of the simulation. Further, then the merger happens at the same time for both the cases. But post-merger, when densities are starting to increase and the crossover region is starting to be reached, that's when we start seeing deviations in the two equations, in the two simulations. 19b stays in 19b collapses immediately to the black hole, whereas 19c stays in the neutron star state for a very extended period and then collapses to a black hole. Same can be seen in our gravitational wave signature. The pre-merger signature, the pre-merger evolution gravitational wave signal is identical for both the cases, whereas for post-merger, there are slight stark differences. And so with that, I want to point out that the main result that we're seeing is that that the post-merger signature is a signal is where we can use to constrain what the high density equational state, the nuclear matter equational state should be. We have performed several convergence tests, and we are still performing more convergence tests for our simulations. And after looking at the spectra, the power spectral density, we noticed that those high density, those post-merger features can be observed by by the third generation gravitational wave of interferometers like the Einstein telescope and Cosmic Explorer. So yeah, with that, I want to conclude by showing my summary and conclusion slides, and thank you all for listening and take any questions.